Imagine you are overseeing a massive industrial production line. Your factory churns out thousands of components, and while you strive for perfection, you acknowledge reality. Some pieces will inevitably be defective. For your operation to remain profitable and your customers happy, you've established a quality threshold. A batch of parts is considered acceptable if the true proportion of defective pieces, which we call P, is no more than 20%. But here is the practical hurdle. You cannot inspect every single component in a massive batch. The time and cost would be prohibitive. Instead, you rely on a sample. You reach into the bin and pull out N pieces at random to verify their quality. This is the essence of statistical inference, using a tiny subset of data to draw conclusions about a vast, unobservable population. Let's look at a specific scenario from our case study. You decide to sample N equals 100 pieces. After testing them, you find that 22 are defective. This gives you an empirical proportion, denoted as X bar, of 0.22, or 22%. Immediately, you are faced with a dilemma. Your observation of 22% is higher than your 20% tolerance limit. If you were looking at this purely as a point estimation problem, you might simply say, the defect rate is 22%, so the batch is bad. But in the real world, decisions are binary. You either ship the batch or you scrap it. And this is where the crisis emerges. Is that 2% difference, the gap between your 20% limit and your 22% observation, evidence of a failing production line? Or is it just the result of sampling luck? Even in a perfectly healthy batch, where the true defect rate is exactly 20%, you wouldn't expect to find exactly 20 defectives every time you pick 100. Sometimes you'll find 18, sometimes you'll find 22. This realization reveals why point estimates alone are insufficient for making binary decisions. We need a way to distinguish between random noise and statistically significant signals. If we reject the batch, we risk a false alarm, throwing away good product. If we accept it, we risk a misdetection, passing on bad product. The goal of this chapter is to build the machinery that resolves this tension, moving from simply asking, what is the proportion, to the much more difficult question, based on this proportion, what should we do? To begin our mathematical investigation into industrial quality control, we must translate physical objects, in this case, manufactured pieces, into a language that statistics can process. We do this by defining a random variable for each piece we inspect. Let's denote the ith piece we pull from the production line as x sub I. Since we are only interested in whether a piece is functional or defective, we use a binary encoding. We assign x sub I a value of 0 if the piece is of good quality and a value of 1 if it is defective. This specific type of random variable, which takes values of 0 or 1, is known as a Bernoulli variable. The behavior of this variable is governed by a single parameter, which we call p. Formally, we say that p is the probability that x sub I equals 1, or p of x sub I equals 1 equals p. In our industrial context, this p represents the true, latent proportion of defective pieces in the entire population of manufactured goods. It is the truth we are trying to uncover, but it remains hidden from us because we cannot inspect every single item. When the factory inspector selects a batch of n pieces at random, we are essentially collecting a sequence of these Bernoulli variables, x1, x2 through xn. To make our statistical tools work, we assume this is an independent and identically distributed sample, or I.ID. Independence means the quality of the first piece doesn't influence the quality of the second, and identically distributed ensures that every piece in the batch is drawn from a population with that same unknown defective rate P. Once we perform the inspection, we move from the world of abstract random variables to the world of observed data. We observe a specific realization of the sample denoted by lowercase x1 through xn. Now, how do we use these numbers to guess the value of the unknown p? The most intuitive approach is to calculate the proportion of defectives in our sample. This leads us to the empirical proportion estimator, which we denote as p hat. Mathematically, p hat is simply the sample mean, x bar. We calculate it by summing up all the x sub I values, which effectively counts the number of defective pieces, and dividing by the total number of pieces n. In our specific industrial example, we observe a sample size n equals 100 and find a sample mean x bar equals 0.22. This tells us that in this particular batch, 22% of the pieces were defective. This process creates a bridge between the unknown population and our tangible data. The inference loop illustrates this. We have an unknown population characterized by p. We draw a sample to calculate an estimate, p hat, and then we use that estimate to make an inference back about the true state of the population. However, we must remember that p hat is a random variable itself. If we had picked a different set of 100 pieces, our result might have been different. Understanding this variability is the key to moving from simple estimation to formal testing. To address the quality control problem, we must understand how our estimator, the sample mean x bar, behaves. Since we are dealing with a large batch, we rely on the Central Limit Theorem. The Central Limit Theorem states that for a large sample size n, the distribution of the sample mean, when properly centered and scaled, converges to a standard normal distribution. Specifically, the difference between the sample mean x bar and the true population proportion p divided by the standard deviation of the sample mean, which is the square root of p times 1 minus p over n, converges in law to a standard normal distribution n 0, 1 as n approaches infinity. This is a powerful result, but it presents a practical difficulty. The denominator contains the very parameter p that we are trying to estimate. We cannot compute a value for this standard deviation because p is unknown. To solve this, we turn to Slutsky's lemma. This lemma allows us to replace the unknown parameter p in the denominator with its consistent estimator, which is the sample mean x bar itself. Because x bar converges in probability to p by the law of large numbers, and the function mapping p to its standard deviation is continuous, the ratio still converges to the same standard normal distribution. This gives us a pivot that depends only on our observed data and the unknown parameter p. Now we can construct a confidence interval. We seek a range of values that will contain the true parameter p with a high probability, say 1 minus alpha. We start with the probability statement that our standardized statistic falls between the lower and upper quantiles of the standard normal distribution, which we denote as q norm alpha over 2 and q norm 1 minus alpha over 2. For a symmetric 95% interval, these values are approximately negative 1.96 and positive 1.96. By multiplying through by the standard error and rearranging the inequality to isolate p, we arrive at the formula for the asymptotic confidence interval. The sample mean, x bar, plus or minus the quantile times the square root of x bar times 1 minus x bar divided by n. Let's apply this to our industrial example. We observed a sample of 100 pieces, so n equals 100. Our observed defect rate was 22%, meaning x bar equals 0.22. Setting our risk level, alpha, at 5%, we use the 0.975 quantile of the normal distribution, which is 1.96. Plugging these numbers into our formula, the standard error is the square root of 0.22 times 0.78 divided by 100, which is approximately 0.041. Multiplying this by our quantile, 1.96, gives a margin of error of approximately 0.08. Thus, our 95% confidence interval for the true defect rate P is 0.22 minus 0.08 and 0.22 plus 0.08, resulting in the interval from 0.14 to 0.30. This result highlights the limitation of using confidence intervals for decision-making. The industrial requirement for an acceptable batch is that the defect rate, P, must be less than or equal to 20%. Our interval, however, spans from 14% to 30%. Because the threshold of 0.20 lies inside this interval, we are left in a state of uncertainty. The data is consistent with a defect rate of 15%, which would be acceptable, but it is also consistent with a defect rate of 25%, which would be unacceptable. While the confidence interval tells us where P is likely to be, it does not provide a formal rule for deciding whether to accept or reject the batch. We need a more binary framework that can turn these probabilities into a definitive verdict. While our confidence interval gave us a range of 0.14 to 0.30, a factory manager cannot ship a batch based on a range. They need a definitive yes or no regarding the batch's quality. This marks our transition from estimation to decision-making. To formalize this, we look at the parameter space, denoted by the Greek letter theta. Since our parameter P represents the probability of a defect, theta is the set of all possible values between 0 and 1. To make a decision, we must partition this entire space into two disjoint or non-overlapping subsets. These subsets are theta 0 and theta 1. In our industrial context, we define theta 0 as the subset of values where P is less than or equal to our threshold of 0.2. Conversely, theta 1 contains all values strictly greater than 0.2. This partition allows us to define two competing hypotheses. The null hypothesis, denoted H0, is the claim that P belongs to theta 0. This typically represents the status quo or the safe assumption, in this case, that the batch meets quality standards. The alternative hypothesis, H1, is the claim that P belongs to theta 1, meaning the defect rate is unacceptably high. The logic of a statistical test is a binary choice. We either conserve H0, meaning we don't have enough evidence to doubt the quality, or we reject H0 in favor of H1. By framing the problem this way, we transform a numerical estimate into a clear, actionable rule for the factory floor. To move from the theory of hypotheses to the practice of decision-making, we must define exactly what data would lead us to change our minds about the null hypothesis. This brings us to the formal definition of a statistical test. A test is fundamentally defined by its rejection region, often denoted by the calligraphic letter R. The rejection region is a subset of the sample space. Recall that our data consists of a sequence of n observations, x1 through xn. This sequence can be viewed as a single point in an n-dimensional space. The rejection region, R, is the danger zone within that space. If our observed data point lands inside R, we reject the null hypothesis, H0, and conclude that the alternative hypothesis, H1, is more likely to be true. Conversely, if our data point lands outside of R, we do not have sufficient evidence to change our minds, so we conserve H0. In practice, describing a complex region in n-dimensional space is difficult. We simplify this by introducing a test statistic, T. The test statistic is a function that takes our entire sample of data and compresses it into a single real-valued number. You can think of t as a summary of the evidence provided by the data. For our quality control example, a natural test statistic might be the total number of defective items found in the batch, or the sample mean of those items. Once we have summarized the data into the value t of x1 through xn, the decision rule becomes a simple comparison. We choose a threshold, or critical value, denoted by c. The rejection region is then typically defined as the set of all samples where the test statistic is greater than this threshold. Mathematically, we write R equals the set of all samples such that T of the sample is greater than C. There is a profound implication here. The outcome of a test is a random variable. Because the test statistic t depends on the random sample, x, the value of t will fluctuate every time we draw a new sample from the population. This means that even if the underlying reality hasn't changed, say the true defect rate p is exactly 0.2, one sample might lead us to conserve H0, while another sample might lead us to reject it. This inherent randomness is not a mistake in the math. It is a fundamental property of making decisions based on partial information. The choice of T and C determines the shape and size of our rejection region, and thus dictates how sensitive our test will be to deviations from the null hypothesis. Once we have defined a rejection region for our test, we must confront a fundamental reality. Because our data is a random sample, our decision to reject or conserve the null hypothesis is also subject to randomness. This means we can make mistakes. In statistical testing, we categorize these mistakes into two types based on the relationship between our decision and the underlying reality. The most critical error to control, and the focus of our current analysis, is the type 1 error. A type 1 error occurs when the null hypothesis, H0, is actually true in reality, but our statistical test leads us to reject it. In an industrial context, imagine a batch of components that perfectly meets the quality standards, with a defect rate, P, less than or equal to 0.2. If we happen to draw an unrepresentative sample that looks particularly bad, we might mistakenly reject the whole batch. This is why a type 1 error is often called a false alarm. We are sounding the alarm for a problem that doesn't actually exist. To formalize this, we look at the probability of rejection given that the parameter p belongs to the null set, theta 0. This probability is not a single number, but a function of p. As p approaches the boundary of our null hypothesis, for instance, as p gets closer to 0.2, the probability of accidentally rejecting H0 typically increases. Because we want a reliable safety guarantee for our test, we define the significance level, denoted by the Greek letter alpha. We say a test has a significance level of alpha if the maximum possible probability of committing a type 1 error across the entire null hypothesis space is no greater than alpha. Mathematically, this is expressed using the supremum. The supremum of the probability of rejecting H0 for all p in theta 0 must be less than or equal to alpha. This alpha represents a guaranteed upper bound on our false alarm rate. By setting alpha to a small value, like 5% or 1%, we are essentially stating that we are willing to accept at most a 5% or 1% chance of mistakenly rejecting a perfectly good null hypothesis. This conservative approach ensures that we only reject the status quo when the evidence against it is truly overwhelming, providing a rigorous mathematical framework for industrial and scientific decision-making. While controlling the false alarm rate is crucial for a manufacturer, it is only half of the story. If we set our standards for rejecting a batch so high that we almost never sound a false alarm, we run the opposite risk, failing to detect a truly defective batch. This brings us to the second type of error in statistical inference. This mistake is known as a type 2 error, often denoted by the Greek letter beta. Think of it as a missed detection. We have a formal definition for this. The type 2 error is a function defined on the alternative parameter space, theta 1. For any specific value of p in this space, beta of p represents the probability that our sample data falls outside the rejection region, R, leading us to incorrectly maintain H0. Mathematically, it is the probability under p that the sample vector x1 through xn is not in R, which is the same as the probability of conserving H0 when it should have been rejected. Closely related to this is the concept of the power of a test. The power, denoted by the capital Greek letter pi, is defined as 1 minus the probability of a type 2 error. While beta represents our failure to detect an effect, power represents our success. It is the probability that we correctly reject the null hypothesis when the alternative is true. In our industrial context, the power represents the sensitivity of the test to detect a truly bad batch. Ideally, we would want both the type 1 error and the type 2 error to be 0. However, we face a fundamental trade-off. For a fixed sample size, these two errors are antagonistic. If you try to decrease the probability of a false alarm by making the rejection region R smaller, you naturally increase the probability of a missed detection because the bar for rejection has been raised. Conversely, if you expand R to make the test more sensitive and decrease beta, you increase the likelihood of rejecting a perfectly good batch by mistake. Because we cannot minimize both simultaneously, the standard statistical strategy is to prioritize the control of the type 1 error. We fix the significance level alpha at a small, acceptable value, like 5%. Once this constraint is set, our goal shifts to finding a test that maximizes the power, or equivalently, minimizing the type 2 error. This approach ensures a guaranteed level of protection against false alarms while making the test as sensitive as possible under that constraint. To bridge the gap between abstract theory and industrial practice, we must determine the exact numerical threshold or critical value that allows us to reject a batch at a controlled significance level. The construction of a statistical test follows a rigorous logical sequence aimed at controlling the type 1 error. Our objective is to define a rejection region, denoted as R, such that the probability of a false alarm, rejecting the null hypothesis when it is actually true, is no greater than our chosen level alpha. In our industrial context, where we test if the proportion of defects, P, is less than or equal to 0.2, the shape of this rejection region is not arbitrary. It is fundamentally determined by the alternative hypothesis. Since H1 posits that P is greater than 0.2, any evidence against the null will manifest as an observed sample proportion, p hat, that is significantly larger than 0.2. Therefore, our rejection region will take the form of all samples where p hat exceeds some critical value c. This leads us to the first major step of our derivation, identifying the distribution of our estimator. Under the Central Limit Theorem, for a sufficiently large sample size, like our n equals 100, the sample proportion, p hat, follows an approximately normal distribution with mean p and a standard error equal to the square root of p times 1 minus p divided by n. To find the threshold C, we must consider the worst-case scenario for a type 1 error. Within the null hypothesis space, where p is less than or equal to 0.2, the probability of p hat exceeding c increases as p approaches p. Consequently, the maximum risk of a false alarm is attained exactly at the boundary of the null space, where p equals 0.2. This is a crucial insight. We calculate our critical value at the boundary because if we control the error there, it is guaranteed to be even lower for any p strictly less than 0.2. In the second step, we formalize this boundary condition. We require the probability that p hat is greater than c, evaluated at p equals 0.2, to be exactly equal to alpha. To solve this, we standardize the variable. By subtracting the mean of 0.2 and dividing by the standard error calculated at the boundary, we transform our condition into a statement about a standard normal variable, z. We are looking for the point where the probability that z exceeds some standardized value is alpha. This value is precisely the 1 minus alpha quantile of the standard normal distribution. For a 5% significance level, this corresponds to the 95th percentile, which is approximately 1.645. Finally, in the third step, we rearrange this inequality to isolate a single value that we can compare against our threshold. This value is our test statistic, t. By taking our observed p hat, subtracting the boundary value of 0.2, and dividing by the standard error, we create a score that tells us how many standard deviations our observation lies away from the null boundary. If this t statistic is greater than our quantile, we reject the null hypothesis. Visually, this corresponds to our observation falling into the shaded tail of the normal distribution curve. This three-step process, identifying the region shape, evaluating at the boundary, and standardizing to find the critical value, provides a universal framework for constructing powerful and reliable statistical tests. With our theoretical framework in place, let's apply it to a concrete numerical case from our factory floor. Suppose we examine a batch of 100 items, so our sample size, n, is 100. We observe a defect rate of 22%, meaning our sample mean, x bar, is 0.22. We want to know if this observation justifies rejecting the batch at a 5% significance level. To make this decision, we follow three explicit computational steps. First, we identify our critical threshold based on the risk alpha. For a 5% significance level in a one-sided test, we look for the 95th percentile of the standard normal distribution. This value, Q norm 0.95, is approximately 1.645. This number represents the boundary. Any test statistic larger than this will trigger a rejection. Second, we calculate the denominator of our test statistic, which is the standard error of our estimator under the null hypothesis boundary, where p equals 0.2. We multiply 0.2 by 0.8 to get a variance of 0.16. We then divide this by our sample size of 100, resulting in 0.0016. Taking the square root of 0.0016 gives us a standard error of 0.04. Third, we compute the final test statistic, t. We take the difference between our observed 22% and the 20% threshold, which is 0.02, and divide it by our standard error of 0.04. This yields a t-value of exactly 0.5. Comparing our result to the critical value, we see that 0.5 is significantly less than 1.645. In visual terms, our result falls well within the white area of the Gaussian curve, far from the blue-shaded rejection region in the tail. Therefore, our formal conclusion is that we conserve the null hypothesis. It is vital to interpret this correctly. A non-significant result like this does not prove the null hypothesis is true. It does not guarantee the batch is good. It simply means that, given our sample size of 100, an observation of 22% is not sufficiently far from 20% to rule out random sampling fluctuation. This decision is strictly tied to our parameters. If we had a much larger sample size, say 10,000 items, and still observed a 22% defect rate, the standard error would be much smaller, and that same 2% difference would likely lead us to reject the batch. The verdict always depends on the interplay between the observed effect, the sample size, and the chosen significance level. To move beyond specific examples and build a robust theory of statistical testing, we must translate our decision-making process into a rigorous mathematical framework. We represent a statistical test not as a set of verbal instructions, but as a measurable function, denoted by the Greek letter phi. This function, phi, maps our sample space to a binary outcome, 0 or 1. The input is our sample of n observations, x1 through xn. The output provides the verdict. If phi equals 0, we accept the null hypothesis, h0. If phi equals 1, we reject h0 in favor of the alternative. This binary mapping condenses the entire complex decision-making process into a single numerical value. This test function naturally defines a specific subset of our sample space known as the rejection region, denoted by a calligraphic R. Formally, R is the set of all possible sample realizations for which our function phi returns a value of 1. Conversely, the complement of R represents the acceptance region. Because of this relationship, we can mathematically define the test function phi as the indicator function of the rejection region. We write this as phi of x equals the indicator of R evaluated at x. In this sense, the test is a switch that flips to 1 whenever the observed data falls into the danger zone defined by our critical values. Representing a test as an indicator function is mathematically elegant because it allows us to use the tools of probability and expectation. The probability that we reject the null hypothesis under a specific parameter value, theta, is exactly the probability that our sample falls into the rejection region. Because phi is an indicator function, this probability is equivalent to the expected value of phi under the distribution governed by theta. This identity, where the probability of rejection equals the expectation of the test function, is a cornerstone of statistical inference. It allows us to calculate rejection probabilities using integration or summation over the test function. We utilize this expectation to formally define the risk of a type 1 error. We define a risk function, alpha of theta, which represents the probability of rejecting the null hypothesis when theta is the true parameter. When theta belongs to the null hypothesis space, theta 0, this function represents the risk of a false positive. However, the null hypothesis is often composite, meaning it contains many possible values of theta. To ensure our test is reliable, we define the significance level, or the size of the test, as the supremum, the maximum possible risk over the entire null space. We say a test has level alpha if this maximum risk is appropriately bounded. The specific nature of this bound, which we denote with an operator, depends on the statistical context. For discrete distributions, we typically require the risk to be less than or equal to alpha. For continuous distributions, we can often achieve exact equality. In large sample scenarios, we look for this relationship to hold asymptotically as the sample size grows toward infinity. When designing a statistical test, the first step is deciding exactly what we are testing against. This choice is formalized by partitioning the entire parameter space, denoted by theta, into two disjoint sets, theta 0 for the null hypothesis and theta 1 for the alternative hypothesis. These sets must be exhaustive and mutually exclusive, meaning their union is the entire space and their intersection is empty. Within this framework, we distinguish between simple and composite hypotheses. A simple hypothesis is one where the parameter is restricted to a single value, such as theta 0 equals the set containing A. In contrast, a composite hypothesis covers a range of values, such as theta 1 being everything except A. This leads us to the two primary structures of tests, bilateral and unilateral. A bilateral or two-sided test is used when deviations in either direction from a target value are important. For instance, in precision engineering, a component might be useless if it is either too large or too small. Formally, we test the null hypothesis that theta equals A against the alternative that theta is not equal to A. Here, the null is simple, while the alternative is composite. On the other hand, we use unilateral or one-sided tests when we only care about deviations in one specific direction. Consider our factory defect rate. We aren't worried if the defect rate is lower than expected. We only want to trigger an alarm if it is significantly higher. In this case, we might test a null hypothesis that theta is less than or equal to A against an alternative that theta is strictly greater than A. Here, both the null and the alternative are composite hypotheses. This distinction is critical because it dictates where we look for evidence in the data, whether we are looking for extreme values on both ends of a distribution or just one. Up to this point, we have evaluated the risks of making a mistake in isolation, considering the type 1 error when the null is true and the type 2 error when the alternative is true. However, in practice, we do not know which state of the world is reality. To truly understand a test's behavior, we need a way to visualize its performance across every possible value of the parameter theta. This is where the power function, denoted by the Greek letter pi, becomes our primary diagnostic tool. The power function provides a unified view of the test's performance across the entire parameter space. Formally, it is defined as a mapping from the parameter space theta to the interval 0, 1. For any specific value of theta, the power function pi of theta represents the probability that our sample results in the rejection of the null hypothesis. Mathematically, pi of theta is the probability, under the distribution defined by theta, that the data vector falls into the rejection region. Because our parameter space is partitioned into the null hypothesis theta 0 and the alternative hypothesis theta 1, we can characterize the function's behavior in two distinct ways. First, consider when theta lies within the null space theta 0. In this scenario, the null hypothesis is true, so rejecting it is a mistake. Thus, in this region, the power function is exactly equal to alpha of theta, the probability of a type 1 error. Ideally, we want this curve to remain low and bounded by our chosen significance level. Second, consider the alternative space, theta 1. Here, the null is false and rejection is the correct decision. In this region, the power function represents the power of the test, the probability of correctly detecting an effect. This is equivalent to 1 minus beta of theta, where beta is the type 2 error probability. Ideally, the power function is low on the null space and high on the alternative space. A perfect test would look like a step function, jumping from 0 to 1 at the boundary. In practice, we look for a steep curve that transitions quickly, indicating a sensitive test that can distinguish between the hypotheses even when the true parameter is close to the null boundary. To understand why formal rigor is necessary, let's analyze a concrete example where intuition leads us astray. Suppose we have a sample of independent and identically distributed observations, x1 through xn, following a normal distribution with an unknown mean theta and a known variance of 1. We want to test the null hypothesis that theta is less than or equal to 0 against the alternative that theta is strictly positive. Since the sample mean, x bar, is an unbiased estimator of theta, a natural first instinct might be to reject the null hypothesis whenever x bar is greater than 0. This seems like a common sense approach. If the data average is positive, we claim the true mean is positive. However, we must rigorously evaluate this naive test by calculating its significance level, alpha. Our first computational step is identifying the distribution of the test statistic. Since each xi is normal with mean theta and variance 1, the sample mean x bar follows a normal distribution with mean theta and a reduced variance of 1 divided by n. This reflects the fact that our estimate becomes more precise as the sample size increases. Next, we calculate the probability of rejection for any given theta in the null space. The rejection region is defined by the condition that x bar is greater than 0. To find this probability, we apply the standard statistical reflex, centering and reducing the variable to transform it into a standard normal z. We subtract the mean theta and divide by the standard deviation, which is 1 over the square root of n. This yields the probability that z is greater than negative square root of n times theta. Using the symmetry of the normal distribution and its cumulative distribution function, phi, this probability is equivalent to phi of the square root of n times theta. Finally, we determine the significance level alpha by finding the maximum probability of a type 1 error across the entire null space where theta is less than or equal to 0. Because the function phi is monotonically increasing, the maximum occurs at the boundary value of theta equals 0. At this point, the square root of n times 0 is 0, and phi of 0 is exactly 0.5. This result is a mathematical disaster for practical testing. A significance level of 50% means that even if the null hypothesis is true and the mean is exactly 0, we will wrongly reject it half the time. This simple rule fails because it completely ignores the variance of the estimator. Without adjusting our threshold to account for sample size and variance, our test is as unreliable as a coin flip. We have no control over our error rate, which is the primary requirement for any scientific or industrial test. To address the unacceptably high error rate of our naive test, we must mathematically derive a threshold that guarantees a significance level of exactly alpha, such as 5%. We begin by redefining our rejection region. Instead of rejecting the null hypothesis whenever the sample mean is positive, we reject it only when the sample mean exceeds a specific positive constant, c. The goal is to find the smallest value for c, such that the probability of a type 1 error never exceeds alpha. We formalize this using the condition of level, the supremum over the null parameter space of the probability of rejection must be less than or equal to alpha. Since our null hypothesis is that theta is less than or equal to 0, we are looking for the maximum probability of rejection across all non-positive values of theta. In our Gaussian model, the sample mean follows a normal distribution with mean theta and variance 1 over n. To make this tractable, we use the statistical reflex of centering and reducing the variable. We subtract the mean theta and divide by the standard deviation, which is the square root of 1 over n. This standardizes our variable into a standard normal distribution, z, which follows a normal distribution with mean 0 and variance 1. By applying this transformation to both sides of our rejection inequality, the condition becomes the probability that z is greater than the square root of n times the quantity c minus theta. Because the standard normal distribution is symmetric and bell-shaped, this probability is maximized when the threshold on the right is at its minimum. Since theta is less than or equal to 0, the minimum value of c minus theta occurs exactly at the boundary where theta equals 0. This worst-case scenario gives us the equation, the probability that z is greater than the square root of n times c equals alpha. Using the standard normal cumulative distribution function, denoted by phi, we rewrite this as 1 minus phi of the square root of n times c equals alpha. Or, equivalently, phi of the square root of n times c equals 1 minus alpha. To solve for c, we apply the inverse cumulative distribution function, often called the quantile function, or Q-norm. This yields the square root of n times c equals the quantile of 1 minus alpha. Finally, isolating c gives us our critical value. C equals the quantile of 1 minus alpha divided by the square root of n. This result is profound because it shows that the critical value is not a fixed constant, but scales inversely with the square root of n. As our sample size increases, the denominator grows, which causes the threshold c to decrease. This means that with more data, our test becomes more sensitive. We can detect smaller deviations from the null hypothesis while still maintaining the same strict 5% error rate. This derivation demonstrates why standardizing is so powerful. It allows us to use universal normal quantiles to set precise thresholds regardless of the specific parameters of our batch. To wrap up our exploration of hypothesis testing, let's synthesize everything into a universal 3-step construction recipe. This workflow is the backbone of almost all parametric statistical tests you will encounter. The first step is foundational. You must define your hypotheses, H0 and H1, and clearly identify the parameter of interest, often denoted as theta. This stage sets the entire context for the experiment. Once the hypotheses are set, the second step is to determine the structure of your test. This involves 2 parts. First, you define the form of the rejection region, R. Crucially, the alternative hypothesis, H1, dictates the direction of this region. If H1 suggests the parameter is larger than the null value, your rejection region will usually take the form where the statistic t is greater than a threshold c. Conversely, if H1 suggests it is smaller, it looks like t is less than c. Second, you need to find a test statistic. Usually, we use a normalized version of our estimator, where t equals the difference between theta hat and theta divided by the square root of the variance of theta hat. This standardization is powerful because it allows us to map our specific data onto a universal distribution. Finally, the third step is to find the specific threshold c that ensures the test has a significance level of alpha. This involves finding the quantile of the test statistics distribution under the null hypothesis, such that the probability of falling into the rejection region is exactly alpha. Let's see this in action with a numerical application. Suppose we set our significance level alpha at 5%. Using the standard normal distribution, we find the quantile for 1 minus alpha is 1.645. If we have a sample size n of 100, this leads to a critical value C alpha of 0.1645. Now, look at the data. If our observed sample mean is 0.1, which is less than 1.1645, we do not reject H0. However, if the observed mean is 0.3, which is greater than our threshold, we must reject H0 in favor of H1. This structured approach moves us from raw data to a mathematically justified decision.